Welcome back, everybody. This is Mr. Johnson with you once again. This is Lecture 15, Part 2, the second half of Section 4.6 on enthalpy. I'd like to take us back to a similar-looking graphic organizer that we saw earlier on in this unit when we talked about the fact that, or I shared with you the fact that enthalpy can ultimately be calculated in one of two ways. Either theoretically, which is what we've been working on, through Hess's law, bond energy or bond enthalpy or heats of formation, and all of those values are in kilojoules per mole. Those delta H's of reaction are always in kilojoules per mole. Or the other option is experimentally through calorimetry, and that's what we've been talking about lately, is this concept of calorimetry. So far, we've only used calorimetry to calculate or understand heat transfers, gain or loss of heat in physical systems. Water warming up maybe, water boiling. Objects heating up and cooling down. And we've been using this Q equals mc delta T equation to do that. Q, of course, is in joules. M is mass, C is specific heat, and delta T is the change in temperature. Then we've also been using this other equation for phase changes. Q is equal to the heat of vaporization, or the heat of fusion times the mass. And out of that comes energy values in joules. What we're going to be talking about today is that calorimetry can also be used to talk about one object transferring heat to another. And as you may know, energy is always conserved, so if one object loses a certain amount of heat, the other object gains that same amount of heat. Water is typically involved in these kinds of problems. So I've written down here, and we'll see this more later, that the Q of the water, the energy change for the water, will be equal and opposite to the energy change for an object. They gain and lose the same amount of energy. And I'll talk about other things about those systems that are important. So that's the first kind of problem we're going to do today. Heat transfers between physical systems where a warm object gives energy to a cooler object, and water is almost always involved. The second half of the lecture today will be about using calorimetry, heat transfers taking place typically in the presence of water, involving chemical systems, chemical reactions that happen in the presence of water. And what you'll see me doing is using Q equals mc delta T to calculate the energy change for the water, knowing that energy is conserved. Whatever the energy change is for the water is equal and opposite to the energy change for the reaction. That'll be in joules, because Q is always in joules. And then we do some fancy calculations at the end to turn that into an enthalpy of reaction in kilojoules per mole. So we're over in this zone of this flowchart here today, finishing out our conversations about calorimetry and enthalpy. All right, so we're now back to our textbook. We're on page 221 of our hard copy book, or 229 of our ebook. And we're looking at this section here that says the first law of thermodynamics, energy is always conserved, which I talked about a bit ago. You saw me write on that flowchart Q equals negative Q. Well, another way to express that, conservation of energy, is to say that the heat lost plus the heat gained is always equal to 0. Or, if we rearrange that equation, to say that negative heat lost equals heat gained. It's important to realize, though, that the heat changes will have signs associated with them. So whenever heat is gained, it's positive. So the sign for heat gained would be positive. The sign for heat lost, of course, speaks for itself. It would be negative. And that's why we need to say Q equals negative Q, so that those values, in fact, equal each other, because they'd otherwise have opposite signs. So a negative times a negative, of course, is going to be a positive. And another way to say that is where heat lost is the total heat lost by the hotter substance, and heat gained is the total heat gained by the colder substance. So the Q of the one system will equal the negative Q of the other. And the other key thing about these problems, and I'm going to solve one with you in a moment, is that when two objects are in contact with each other, and one is hotter than the other, the heat always travels from the hotter object to the cooler object through molecular collisions until they, on average, have the same kinetic energy, until, on average, they are at the same temperature. So not only will the heat lost equal the heat gained, once enough time has elapsed, and we assume that that's the case in our problems, they reach what's called thermal equilibrium, and they will reach the same final temperature. So two key concepts in these problems. The heat lost equals the heat gained, but with opposite signs, and the objects, as long as they're in contact for enough time, reach thermal equilibrium / their final temperature will be the same. And you're going to see me address that in a sample problem we'll do here in a moment. And that sample problem is on this same page here. It's a sample problem on page 229 of the ebook, or 221 of our textbook, and I'm going to go to a whiteboard here and solve that problem with you. So here's our problem. We've got 50 grams of water at 15 degrees Celsius being added to 40 grams of water at 85 degrees Celsius. It's asking us what's the final temperature of the system. We should know when two objects are added together and they're at different temperatures, which these are. There will be an exchange of heat. The hotter object will lose heat, the cooler object will gain heat, and the amount of heat gained and lost will be equal and opposite to each other. And again, the final temperature these two objects reach, in this case they're both water, will be the same temperature. So the final temperature of the system will be the temperature of the cool water and warm water once thermal equilibrium is reached. The first thing I've done is acknowledge the conservation of energy, which is the Q of the cold water equals negative Q of the hot water. Actually, it doesn't matter where that negative sign is. I can flip it back and forth, but the cold water is gaining energy, so I could think of it right now as a positive Q, and the hot water is going to be losing energy, and I can think of it as a negative Q, and again, those values will be the same. The next thing I've done is written what I know Q to equal, which is mc delta T for both the cold water. So I've said that the Q for the cold water is equal to the mass of the cold water. CW stands for cold water times the specific heat of the cold water times the delta T of the cold water. And for the hot water, I've said the same thing. Hot water, mass, specific heat, and delta T. And I forgot to put my negative in there. And again, that negative could be on either side, but it makes sense to have it with the hot water since it's losing the heat energy to the cold water. Since this is water on both sides, and the specific heat of water on both sides is the same, to make the algebra a little bit simpler, I can just cancel out or cross through C of water since it's the same on both sides. I'm going to rewrite that without C of water. So I've rewritten that without the specific heats in there because, again, they're the same, and I can cancel them both out. Because in this case, I'm finding the final temperature, which is, by the way, the final temperature of the cold water and the hot water. They will be the same because it does reach thermal equilibrium. I can't calculate delta T for either of these. I can't plug delta T in for either side. So what I'm going to do is rewrite this equation now with what delta T is equal to on both sides, the final temperature minus the initial, so I can then start plugging my values in. So what I've got now is the mass of the cold water again. I've substituted in for delta T the final temperature of the cold water minus the initial temperature of the cold water. Remember, delta T's are always final minus initial. Same thing on the other side. Here's the mass of the hot water carried down, and then substituted in for the delta T of the hot water as the final temperature of the hot water minus the initial temperature. I'm now ready to plug all these values in that were given to me into the problem, minus the final temperature, which will be the same on both sides. So when I rewrite this with the values plugged in from the problem, I'm just going to say TF on both sides because it's the same TF for both the cold and the hot water. So that cold water had a mass of 50 grams. That's there. Again, I've written TF on both sides because it is the same final temperature. And the cold water had an initial temperature of 15. Hot water started out at 40 grams, or is 40 grams, and started out at 85 degrees Celsius. So I plugged in all my values for my problem, and I'm now ready to do some algebra and solve this. So the first algebraic step I took is I distributed 50 into both terms. 50 grams times TF is 50 gram TFs. Units are a little weird. It's okay. And then 50 times negative 15 degrees Celsius is negative 755 grams times degrees Celsius. Right side did the same thing, distributed negative 40 into both terms, negative 40 gram TFs, and then negative times a negative is positive 3,400 gram times degrees Celsius. Next thing I'm going to do is combine like terms. I'll combine my gram degrees Celsius with my gram TFs, and then isolate TF and get it by itself, and the final answer. So I added 40 gram TFs to both sides so that these would cancel. We're going to end up with 40 plus 50 gram TFs over here, and I added 755 gram times degrees Celsius to both sides to get them to go away from the left. So I'll add these up, do some canceling, and see what we get. So on the left, I've got 90 gram times TFs. These canceled. On the right, I've got 3,400 plus 755, 4,155 gram times degrees Celsius. I now want to get TF by itself, so I'm going to divide both sides by 90 grams. Divide both sides by 90 grams. That goes away. My grams cancel. I'm left with the degrees Celsius, and 4,155 over 90 is 46.2 degrees Celsius. Let's see if that answer makes sense. Let's go to the top and see if it makes sense. So again, we got 46.2. There's a lot of ways mistakes can be made, lots of signs that you've got to pay attention to. The temperature should be between 15 and 85, and it is. And if the mass of the cooler water is greater than the mass of the warmer water, the temperature should be a little bit closer to the cooler water than the warmer water, since there's more water in that cooler bit. And 46.2 is a little closer to 15 than 85. So the answer looks right, and I'm pretty sure it is. Well done, folks, following me along. We'll do one more. I'll ask you to solve it first, and then you can come back after you've solved it and see how your solution compares to mine. So we flipped our page. We're on 230 of the digital book, 222 of the hard copy book, and it's practice problem 2 on this page that I would like you to try to do on your own. It's similar to the last problem, but this time we're going to find the mass of the brass ball bearing, and we're given the final temperature. So it's a little bit easier algebraically. Give this one a shot. Come back when you're done and see how your solution compares to mine. All right, so I know this is an energy transfer problem with the Q of the water equaling negative Q of the brass object. Again, it wouldn't matter where the negative is, but the brass object is losing energy, so I gave it the Q. I substituted in for Q, mc delta T for both objects. Water's on the left, the brass object is on the right. The water's mass is 125 grams, specific heat of liquid water 4.18 joules per gram degree Celsius. And the water ends at 2655. Both objects do, remember. In these kinds of problems, they'll end at the same temperature, and the water started at 20.5. The mass of the brass object is what we're solving for, so that's MB. Brass's specific heat I grabbed from my book. It's 0.380 joules per gram degree Celsius. And then the delta T is the final minus the initial. Again, the brass ends at the same temperature as did the water, 2655, but it started at 9555. So on the left, I just multiplied all that out, and I got 3161 joules. That is the product of everything on the left. And on the right, I got the mass of the brass object times 0.380 times 26.55 minus 95.55. And those two negatives turned it all into a positive. So that's the product on the right. I then divided both sides by 26.22 to get the mass of the brass object by itself. And when I do that, joules cancels, and I get the inverse of grams, or grams, and the mass of the brass object is 121 grams. All right, we're back to our book. We're on 230 of the ebook, or 222 of our textbook, and we're looking at the section called Coffee Cup Calorimetry, or Calorimetry. Little side note, a calorie on our food labels is actually a kilocalorie. The FDA, the U.S. Department of Agriculture, didn't think we could understand what a kilocalorie was, so they labeled our food labels with calories. But in Europe, food labels are labeled with kilocalories. So if you eat 100 calories, it's actually 100,000 calories or 100 kilocalories. Well, 1 kilocalorie equals 4.18 kilojoules, because hopefully remember that 1 calorie is 4.18 joules. So that's what calories are. And a calorimeter, which we'll talk about in a moment and see a video of in a moment, is a device that is used to measure through energy transfers energy changes that take place in chemical reactions or in physical processes as well. So we're going to go to a Bozeman science video because Mr. Anderson explains it well, and he's got some nice imagery that I was unable to find.
And that's really how a calorimeter works. All you have is you're going to have a vessel where we're going to have that reaction or that heating or that phase change occur, and then we're just going to have it sitting inside this heat bath. We can measure the changes in temperature. And by measuring the changes in temperature of the water, we know how much energy is being released from that vessel or being consumed by that vessel. And so if we heat up that material in there, let's say it's a chemical reaction, and we see changes in the temperature, we know how much of that is coming from the reaction inside that vessel. And so this is what this would be a bomb calorimeter, and what it's doing is we're putting whatever we want to study inside this vessel, we're enclosing it inside water, we have a really detailed thermometer on the inside. Lots of times they'll have a stirrer so that we're moving that water around, and we can measure energy changes. We could use that to measure specific heat capacity, enthalpy of fusion, that's when we're going, remember, from a solid to a liquid or backwards. We can measure enthalpy of vaporization as we're going from a liquid to a gas, or we can just measure that enthalpy of reaction. We can measure endothermic and exothermic reactions. And so that's the role of a calorimeter. And so could you design or interpret the results?
All right, thanks for that, Mr. Anderson. So we see in our book, we've now flipped our page. We're on 223 of the textbook, 231 of the ebook. Couple of calorimeters up here. Oftentimes it's just a styrofoam cup. In fact, if we were in lab, we'd be using styrofoam cups for calorimetry, which is why it's often called coffee cup calorimetry, or you can have a fancier system that's a little bit better insulated. The idea is that a lot of processes take place in water anyways, or can. A lot of chemical reactions take place in water, or they can. And if we have a process or reaction take place in the presence of water, and we monitor the temperature of the water and its mass, like Dr. Anderson said, we can do some cool calculations to figure out the energy change for that process and figure some other fancy stuff out about it. Same idea as before when we're using calorimetry for chemical processes instead of physical processes, which is what the last two problems were about. Objects just heating up and cooling down is physical. Conservation of energy still comes into play. Heat lost plus heat gained will still equal 0. Or Q for reaction is going to equal negative Q of water. Same idea there. However much energy the water gains from the reaction is equal to the energy the reaction lost, or however much energy the water lost is equal to however much energy that reaction gained. So we're still on this same page, and I am going to solve this sample problem nice and slowly with you on my whiteboard again. And then like last time, we'll give you one more problem to try on your own and to come back after having paused the video and see how your solution compares to mine. So we're doing this sample problem here on this same page. All right, if it's late or you're tired or you're feeling fatigued, I recommend you stop the video, come back later when you're feeling a bit better, because this is a wonderful problem that deserves your full mental attention. All sorts of great stuff going on in this problem. All right, I'm going to read it to you. A neutralization reaction between 50 milliliters of a 1 molar HCl solution and 50 milliliters of a 1 molar sodium hydroxide solution is performed with constant stirring at room temperature, 20.5 degrees Celsius. The temperature rises to 27.13 degrees Celsius. You are supposed to know that acids and bases are already dissolved in water, so this reaction is taking place in the presence of water because the HCl and sodium hydroxide are already dissolved in water. So we actually have 100 milliliters of water this reaction is taking place in. And that water and both of the reactants started at 20.5 degrees Celsius, and the water ends up at 27.13 degrees Celsius. So 100 milliliters of water went from 20.5 to 27.13 through this neutralization reaction. Assume the solution volumes are additive, meaning that 50 plus 50 will be 100. There's no loss or gain of volume. And that the density and specific heat capacity of the final solution is the same as those values for water. Meaning even though there's HCl and sodium hydroxide dissolved in this aqueous environment, assume that the specific heat will still be 4.18 joules per gram degree Celsius. Yes, the presence of other things dissolved in water alters the specific heat slightly, but assume it's negligible and that the specific heat again will be 4.18. Also assume that the density of this water, even though there's HCl and sodium hydroxide dissolved in it, is 1.0 grams per milliliter. So if you've got 100 milliliters of water, even though there's stuff dissolved in it, assume that the density is 1, and that 100 milliliters will equal 100 grams. And I'll go back over that in a moment. Only assume a negligible amount of heat is absorbed or released from or to the surroundings. And in all these calorimetry problems, we assume that the heat transfer that takes place from the reaction to the water is perfect, that no heat gets lost to the air. And that's just an assumption you have to make, even though in reality that's difficult unless you're in a really fancy bomb calorimeter. And in the end, we're going to find the molar enthalpy of neutralization, the enthalpy of this reaction. All right, here we go. Although we don't need it for a little bit, the first thing we should do is write out a complete balanced reaction between HCl and sodium hydroxide. So HCl, which is aqueous, will react with sodium hydroxide, which is also aqueous. It's a double replacement reaction or neutralization reaction to form sodium chloride, which is soluble, and liquid water. And it doesn't need balancing. So there's my balanced reaction. I'm going to write the values of the HCl and sodium hydroxide underneath just so it's easier to keep track of. They're both 50.0 mils. And they're both 1.00 molar. Okay, so we'll come back to the reaction in a moment. First thing we need to do in a problem like this, where a reaction takes place in the presence of water, is calculate the Q for the water, what the energy change is for the water. We're going to MC delta T the water. So Q for water is equal to M times C times delta T. The water is the 50 mils of water from the HCl combined with the 50 mils of water from sodium hydroxide, because that 100 mils of water is what's undergoing the energy change. And 100 milliliters with a density of 1 gram per milliliter is 100 grams. So we got 100.0 grams of water. Liquid water's specific heat capacity is 4.18 joules per gram degree Celsius. And the temperature change the water undergoes is 27.13 degrees Celsius minus 20.50 degrees Celsius. And all of that, when multiplied out, is 2,771.34 joules. Should be positive because the water is increasing in temperature. And if the water is gaining energy, that means the reaction is losing energy, which means the reaction is exothermic, which we should know is what neutralization reactions always are, is exothermic. All right, so now we apply the law of conservation of energy, which says that however much energy water is gaining has to be equal and opposite to the energy the reaction is losing. So I'm going to say Q for Rxn is equal to negative 2,771.34 joules. And that's because the Q of the water is always equal and opposite to Q of Rxn. It's really important to make a sign switch here, that when you go from the water in a calorimetry problem to the process or the reaction, you switch the sign or things get messed up later. So the reaction's Q is negative 2,771.34 joules. All right, so that would be our final answer if all it asked us to do was to calculate what the energy change in joules is for this particular amount of HCl and sodium hydroxide. But when we're asked to calculate an enthalpy, a delta H of neutralization, the unit is always kilojoules per mole. So we cannot publish this answer in joules. It's got to be in kilojoules, and it has to be per mole of limiting reactant. And we don't have 1 mole of either of these reactants, nor are joules kilojoules. So we've got to convert this from joules to kilojoules per mole. The first thing I'll do is figure out how many moles of the limiting reactant it is we have. Since we have equal volumes of both reactants, and their molarities are equal, and they react in a 1-to-1 ratio, neither reactant is limiting. We have the same number of moles of both. If you multiply the volume by the molarity of both these reactants, it'll be the same. And they react in a 1-to-1 ratio. So for either reactant, I can multiply the molarity by the volume to get the number of moles. I'll do that right now. So I've done that in red up here. The 1 molar HCl solution is 1 mole per liter, and if I multiply it by 50 milliliters or 0.050 liters, I get 0.05 moles. And again, it would be the same for sodium hydroxide, and since they react in a 1-to-1 ratio, that's why both or neither are limiting. Okay, so now I need to take this Q that's in joules, this negative 2,771.34 joules, and convert it first to kilojoules, because enthalpy is always in kilojoules per mole. 1 kilojoule is 1,000 joules. And then I could do this and get kilojoules, and then divide by 0.05 moles to get the number of kilojoules per 1 mole, not per 0.05 moles. Or, because dA can be used for math or for algebra as well, I can just go 0.050 moles down on the bottom. Same thing as dividing by moles. And joules cancels, and I'll be left with kilojoules per mole. So if I take negative 2,771.34, divide by 1,000 and by 0.05, I will get the enthalpy of reaction. Let's see what that is. And there we go. It's negative 55.4 kilojoules per mole. The sign being important, this is an exothermic reaction. It's releasing that much energy. So again, in this last step here, and that's that really important, crucial thing about delta H is always being in kilojoules per mole, is I had to convert joules to kilojoules, and then I divided by the moles of the limiting reactant in the end and got the kilojoules per mole. All right, so we're going to do one more problem. I'll encourage you to do it on your own, and then I'll solve it, and you can check your solution. So we're going to be doing practice problem 2 on page 224 or on 232 of your ebook. All right, so here it is, practice problem 2 on 224 of your textbook. I'll get you thinking about it, how you might solve it, and then suggest you pause me and come back after you're done. A coffee cup calorimeter contains 50 grams of water at 20.73 degrees Celsius. All right. It's the initial temperature of the water. When 2.13 grams of ammonium nitrate pellets are stirred into the water, the temperature falls to 17.41 degrees Celsius. Looks like water is going down in temperature, water is losing energy. Q will be negative for water. The system is going to be gaining energy, endothermic. Assume the heat capacity is the same of water, like last time. Assume it's 4.18, even though there's stuff dissolved in there, and that no energy is absorbed or released from or to the surroundings. And even if it doesn't say that, assume that's the case, that it's a perfect energy transfer. Calculate the molar enthalpy of dissolution of ammonium nitrate, a chemical commonly used in the production of cold packs. So we're going to do the same thing here. We're going to MC delta T the water. We're going to switch the sign and attribute that energy to the process. We're going to write out the reaction, the dissociation reaction of ammonium nitrate into its ions, figure out how many moles of ammonium nitrate that is, and then convert our joules to kilojoules, divide by moles, and we're done. So give that a shot. Come on back and see how your solution compares to mine. All right, just to shake things up a little bit, I thought I'd go with the Q equals MC delta T first. So I did that for water. The water's mass in this case is 50 grams. Specific heat, again, is 4.18 joules per gram degree Celsius. We assume that the specific heat of the water, even if it has some stuff dissolved in it, is that of water unless we're told otherwise. Final temperature, 17.41. Initial temperature, 20.73. All of that multiplied out is negative 693.88 joules. Sign makes sense because the temperature of water is dropping. I then say that the Q of the water is equal to the negative Q of the reaction. That's a really important thing to acknowledge, and the sign switch is important to do. When you go from the water to the process, switch that sign. Then I wrote my reaction. This is a dissociation reaction of ammonium nitrate being dissolved in water. So ammonium nitrate, when it's dissolved in water, dissociates into its ions. That reaction wasn't crucial to write because all there is one reactant, all there is ammonium nitrate, and all we have to figure out is moles of that, but it's a good time to write a reaction anyways. So I divided ammonium nitrate by its molar mass of 80.08 grams, and I got 0.0266 moles of ammonium nitrate. Then I convert the joules to kilojoules by dividing by 1,000, dividing by the number of moles of ammonium nitrate, so that my answer is the way it should be, which is in kilojoules per mole. So it's 26.1 positive kilojoules per mole as the enthalpy of dissolution for ammonium nitrate. And what that means is that when ammonium nitrate is dissolved in water, the system gains energy and the water would cool down. So if you actually had your hand in water that ammonium nitrate was dissolved in, the water would feel cooler because the water is giving its energy to the system, the ammonium nitrate. That's it, folks. Lecture 15, Part 2 has come to a close. Mr. Johnson signing out, and I hope you have a nice morning or afternoon or evening or whatever it is that is in front of you on this beautiful day. See you soon.